Can you bring the light back on? Thank you. Okay, so that first one, it wasn't too bad. Normally, with these, you of course want to start with some idea of what it's going to do. So what gives us an idea of what this is going to do? Yeah, I mean, you have to get comfortable with the fact that this is letting n get really, really big eventually. So eventually it's going to look like that. That's not good enough for any explanation of anything, but it just gives you a gut feeling it's going to be, it's trying to be 1 over n. So you could do direct comparison, right? But slightly better than that. Yeah, you could do the limit comparison. So how would that get set up?
That times
Here's my an. I want to, of course, compare it to 1 over n. And that's what came out of my reasoning as just to get a feel for what I was going to do. So if I do that, good, times n. And of course, you're going to get n cubed. So what's this limit going to be? 1. And limit comparison is all about the result has to be where for to say something. Good. So this is in between 0 and infinity. I like it. So what does that mean? Yeah, so the limit comparison is interesting. It's the one that tells you if the result's between 0 and infinity, then the two series you're looking at do the same thing. Since that diverges, then this must diverge. Keep going. All right.
Can we skip the 17?
Okay, 17's a neat one. We can do that. So what do you guys think about number 17 here?
I think I wanted to use direct. So I think we need to get rid of the cosine. So I was thinking the direct comparison, we're going to plug it off by turning it into 4. Or no, 2. No, wait, never mind. We wanted to say 4, but then we think that's going to diverge because it's greater than 1. The R is greater than 1, so we want to find 4.
So what's the R you're looking at? Is everybody kind of with what's happening? If that wasn't there, if it was this, and then effectively you can say, well, that wasn't there. This is just getting a feel for what this thing looks like it's trying to be. Of course, cosine 3n also has the interesting property that it's sometimes negative, sometimes positive, but we'll take care of that in a minute. What kind of thing is that trying to be? Kind of give it away there? Because you can make 1 to the n anytime you want to, right?
Yeah.
Same damn thing. So that looks geometric, but 1 over 1.2 is less than 1, right? Because when you have a geometric, you're looking at your r, and as long as your r is less than 1, then you know it's going to converge. So let me stop there for a second. So if I think this is going to converge, period, then I want to go straight to absolute convergence, right? Very often I want to do one of the two extremes. Either divergence and I'm done, or it's absolutely convergent and I'm done. But if I think it might converge and then it's not absolutely convergent, then I got to do even one more thing. I got to see if it's conditionally convergent. That doesn't happen all the time, but that's a very classic kind of way to go through these. So it looks to me like it's going to converge, right? So yeah, we could try to do some kind of comparison test, maybe a direct comparison test to get rid of that cosine, right? And I'm going to look at the absolute value, just to go straight to absolute convergence. Why am I doing the absolute value? Yeah, then why do I want to go straight to that? Because the cosine's got a little weirdness to it, right? That's one reason why it's nice absolute convergence idea exists. Because I got some weird, I'm not sure how it really alternates. Okay, so so if I think this converges, I want a ceiling or a floor? Ceiling, push me down. So I want to get something that's bigger than me. So a little bit better than the other one we did. What is always bigger than this? Huh? Sure, you could say 4. Sure, that's true. Or, what's always at least as big as that? Let's say like 1. Yeah, the biggest cosine can be is 1. Don't let that 3 freak you out. Is that 3 freaking you out? Doesn't matter what I plug into a cosine, its output's going to only be between -1 and 1. And I got the bottom here. Now, how do I make, does the inequality go the right direction if I just take that 1 away? If I take that 1 away, do I end up with something that is bigger?
Yeah. Yes.
Yes, good. So then I'm allowed to do that. And what did I just uncover? The thing that I knew this was trying to be. So what kind of series is this? Geometric. And what kind of geometric?
Convergence.
All right, that's the one. So it's convergent. This series converges with absolute values on the damn thing. So my series absolutely converges. Yeah.
Even 4.
I like that 4. Why'd you put a 4 in there? It'll still work with a 4. Then what the hell?
I was thinking the 3 on the outside, so I was thinking.
They were thinking.
Oh, okay, gotcha. I understand. Like amplitude of 3. Okay, gotcha. But it'll still work. Okay, so let's do some in-between ones here. What about 13? How'd that go? This is a little weird. You can't quite do what you want to do. If that n cubed wasn't there, you could. N cubed doesn't grow nearly as fast as 5 to the n, so you kind of know what this thing is going to do. Possibly, right? N cubed still grows bigger than any constant would, so it's not necessarily directly a geometric. But what's a good idea to use exactly? When I have an exponential piece to something, I could try the ratio test and see if that goes anywhere. And the ratio test involves doing what? The next term divided by the previous term. I like it. So what's a n plus 1?
N plus 1 is 5 plus 1.
Alright, so then I look at the limit. N goes infinity of what? I love it. So it's going to be this guy times
5
beautiful, the reciprocal. Now, please don't do too much work here. The degrees on the top and bottom will be the same, so the limit of this piece will be 1. I love it. Just don't, there's no reason to foil that thing out. Don't do that. The most important thing with that, and if you do, it's not horrible, but it's just the degree comparison you want to do for that, right? So that piece is 1. What happens between these two?
You just get a 5 on the bottom.
Yeah, you got an extra 5 here. So this limit's going to be 1 over that extra 5, which the important thing for the ratio test is that is less than 1, which means this is absolutely convergent. Be very careful. You got to be more specific about your convergence now. Right. Okay. Let's see, number 14. I don't think I saw most people doing that. We're doing it pretty good. That one definitely comes out conditionally convergent. Right? Taking that -1 out is obviously a p-series with the 1/2. So I'm going to skip that one. Everybody I saw doing that was doing it okay. 15 we talked about earlier. That's an integral test. And for anybody who did that integral test, how does that come out? Yeah, it should be divergent. I don't know if you remember that natural log with the weirdness of the natural log. This thing diverges, but the minute I make 1.00001, it's going to converge, right, that series? But if I multiply n by ln, this is not even enough to push it over that edge. So if I multiply by square root of l, that's even
smaller.
Exactly, right? So you kind of know how this is going to come out, but you still got to do it to show it to be official. The integral of this shouldn't be too horrible, right? Just don't forget to make it into real numbers. Cool, you get the integral of 1 over square root of u, basically, which is going to be u to the 1/2, basically, minus constant. So that's definitely going to go to infinity. That's divergent. Is everybody decent with that? We've done integrals like this a lot. So once you identify it as an integral test, that should be pretty quick. 16 is also, please, dear God. I haven't been saying this as we've been doing these because they were kind of obvious, going to converge or diverge. this problem, number 16, and in general, what do you always want to try to do first? Yeah, test for divergence. Especially if you're not sure what the hell it's going to do at all, you just test for divergence right away. And sure enough, what happens when you let n go to infinity here? Yeah, that can come inside because this is continuous. So you get ln 1/3, which I don't care what it is, I just know it's not 0. So this guy has no chance. So it's completely divergent. Cool. I like it. I like it. Okay. And then 18, what would you do on 18 if you didn't get there? Look at 18. What would you apply to that? Beautiful, right? And to rewrite this up here, how could you rewrite n to the 2n? When do you multiply powers? When you raise something with power to the power. That just kind of pulls that nth power out a little more prominently, and then you can kill it on the next step when you take the root. Okay, cool. I'm desperately trying to get us to a point where I can get to the next section. And number 19 looks like they kind of give it away there a bit on number 19, if you got there. I'm going to let that one be until next time. Let me give you this next little handout. Actually, let me ask you this question. There was a homework question a while back about one of these series, and they had an x value in it. And they were asking about what x had to be for this to converge. So if I put something like this down, we already know what's got to be true. So x is everyday x. It could be anything it wants to be. But what would we have to make it in order for this to converge? Yeah, because what kind of series is this trying to be? Geometric. Geometric. I love it. You guys kind of with me? Now, just to prove that, just to really show that, we could apply what test to this, do you think? Let's try the ratio test. I like that. So how do I do the ratio test here? Good, good. So it's the next term.
X plus 1 over x.
Be careful now. What are you letting go to the next element? What's increasing by 1? N. My x, I wouldn't change that. It's some given number. You with me? You're going to look into the next term, which would be n plus 1. So x to the n plus 1 over, of course, so it's that. And what's got to be true for this to converge? If we're doing the ratio test, the result has to be what? Less than 1. Isn't that what we just said earlier? All right, so it's always nice to kind of go into something knowing what the answer is supposed to be, just so you kind of buy into it. The newness of this is that we now have a part of our series that's not been identified. It's just an x. It's a variable. So what we can do is we can figure out what kind of values could I put in for x that would let my series converge.
Do you also do the root test since it's raised to
I was waiting to see if you did the root test, can you see how the same thing would happen? The nth root of this would be x, absolute value, less than 1, same outcome. I like it. Cool. Now, on top of this is kind of like a very, very basic example of something called a power series. So, you know that math people were very creative. So when we see this, x is being raised to powers, we call it a power series. So you can see why we do. But the more general, to make this a little more general, a power series could look like this. So, for example, in this one, a is 0, And every coefficient for every element is 1 in this example. But here I could have coefficients based on n. And I could also have not just x, but I could have x minus 1, x minus 2. So this is the most general form for a power series, where things get really interesting. And I keep talking about this every now and again, that we're headed towards what's called Taylor series, Taylor polynomials. And some of you guys knew about those coming in. That's where you make this something very, very specific for a very important reason. So we're almost there. So it's really just this with these defined in a very special way. That's going to be section 1110. But if I had, let me give you this here so I can talk about some of these problems on here. All right, so the very top part basically says what I just said. It kind of lays it out for you. Some of the examples I give are sort of like what I just gave here, just in reverse. So if I let x be a specific value, I can kind of analyze that series. But we want to be more general than that. We want to go the reverse way. I don't want to make x something specific. I want to let x be x, but then figure out what values would allow it to converge. So I have an example down there that's kind of obvious about how it works out. But if I had this, so over here, x had to be less than 1 to converge. Is there any reason to believe that this might converge differently? Will it be easier or harder for this to converge?
Harder.
Why harder?
And factorials will be a lot bigger.
But where is it?
It's on the bottom.
So all my elements are going to be much smaller than they were before, right? So we could do the exact same thing we just did over there earlier. We can apply what kind of test? Yeah, why would root test not work well here, necessarily? Yeah, not everything is to the nth power, so it doesn't really help me out. Nth root of this, I don't even want to think about. So how would I apply the ratio test here? Ratio test is always involving the ratio of what, two things? Yeah. So what's the next element?
X to the n plus 1. N plus 1 factorial.
And this is why I was talking about that factorial, being really comfortable with how to work with it, because this is going to happen a lot to us. Good. Times the reciprocal of that, because I want to divide by an, so I multiply by its reciprocal. And this is, what have I left out of here? It's kind of important.
X to the x.
I've left out absolute values. Good. Because this is actually a test. Ratio, root test, they have absolute values. They're tests for absolute convergence. So what happens with all this stuff? What can I do with the factorials? Good. So I can take this down to... Yeah, I know when to stop. When it matches with something that's there. So we were doing this the other day. It's kind of like it here. So then this n factorial goes away. And of course here, good, I have an extra x up here. So nx is canceled. So what am I left with here? Let's take a look. I have, on the top I got x. And what do I have on the bottom? N plus 1. Yes, sir?
Can you explain when you use the absolute values and use them for the units test?
So the ratio test and the root test are tests for absolute convergence. So they have the absolute value included.
Testing for absolute convergence.
Exactly. And it's because of the fact that they're built off of an assumption about you're looking at positive terms. You have to build in that absolute value to make that true. And we've used that when we had cosine n. We had to use absolute values so we could talk about positive terms and use other tests. Somebody tell me something about this. Does it?
Zero.
Yeah, this is 0. Does it depend on x? Does it care what x is? No. So this result is not dependent on x. So no matter what x is, the result is, what's important for this test? The result is? It's 0. Less than 1. I love it. No matter what x is, it's less than 1. That's different from what we had up here. This one said that the absolute value of x had to be less than 1. So what do you think this means? What could x be to let this thing still converge? If it goes to 0 no matter what,
It could be whatever.
x could be whatever. I like it. So a little bit on that. It says what's called the radius of convergence. I like this idea because it kind of like starts at 0 and goes out from there. So the radius of convergence in this case would be, since it's everything, it's from negative infinity up to infinity. I love it. So obviously we still have a lot to cover on that handout. So we'll pick up from there next time. I'll see you guys next week. Have a good weekend.